Good afternoon, Fosdem. So, as I was introduced, I'll be talking today about the status of ARM support in the Linux kernel. Of course, I could be talking about this topic for many, many hours. So in just 50 minutes, I'll just be giving a very high-level overview of what are the main changes that have been taking place since the last 1 or 2 years inside the Linux kernel to support ARM platforms. So briefly, I work for Cree Electrons, and the main reason I'm talking to you about this topic today is because we work under contract with Marvell, who is a maker of ARM SoCs that are very common in network-attached storage devices. So we do for them the Armada 370 and Armada XP support inside the mainline Linux kernel. So those are two new ARM SoCs, or relatively new ARM SoCs. And besides that, I also contribute to another project called Buildroot. So today, I'd like to share first some background information about the ARM architecture and the Linux support for it. I'm not sure if the entire Fosdem crowd is very familiar with how the ARM architecture works or is organized and how it differs from the x86 architecture. Then I'm going to show some of the issues that the Linux support for ARM had inside the kernel, and see the main changes, or at least what I see as being the main changes that occurred in the last few years in the ARM kernel support in Linux. And I'll show also, in more specifically, what we've done to support the ARM 370 and XP SoCs to see what kind of work is needed to add inside the mainline Linux kernel the support for new ARM processors. So first, to understand the ARM architecture, it's very important to understand how the chips are well designed and how it comes down to the board or the system that you have in your home or in your office or in your industrial application or whatever. So to make it simple, and I know there are some ARM employees in the room, to make it really simple, ARM, the company, does not sell any chips. They design an architecture, so they define an instruction set, they define how a memory management unit works, they define how the interrupts are handled inside the CPU, and everything that's really inside the CPU, and that's only a kind of specification. They describe, we will support this instruction with this behavior, the memory will behave this way, and so on and so on. From this definition, they implement ARM cores. So they do an implementation, typically in Verilog, of such specification. And then they sell this Verilog code or some other derivative form of that to silicon vendors. So ARM is not selling processors. It is selling a specific implementation of a given ARM core to a silicon vendor. So silicon vendors being companies like TI or Freescale or Marvell or Broadcom or many, many others. They have hundreds of licenses. And what do silicon vendors do? They create a system on chip. So they take one specific ARM core, or sometimes several of them, and they combine them with additional peripherals, simple peripherals like serial port controllers, network interfaces, graphic controllers. There has been just before a talk about 3D graphics acceleration. They can bring peripherals like 3D graphics accelerators. They can add, I don't know, any other type of input-output interface, Ethernet, CAN, RS-232, RS-485, and many other types of peripherals to make the system on chip specific to a given market. So some silicon vendors do chips for the industrial market with lots of IOs. Some other silicon vendors do chips for the multimedia industries with a lot of video encoders, decoders, 3D accelerators, and so on. Some other silicon vendors will do chips for the automotive industry, some other for different markets. So depending on the ARM core you choose, depending on the peripherals you add, you target the chip to a specific market. And then down the line, there is a board maker or a system maker that builds this system on chip, because now it is a physical chip that you can actually buy. And it puts it on a PCB and integrates some other components around it to interface with the outside world, add additional components as needed. So it's really important to understand this chain of elements that takes place in every ARM system that you buy, because it's one of the reasons why the support for the ARM architecture is seen as so complicated by many people. So if we take some examples of those like 4 stages, and again, it's kind of a simplified vision of it. I took the example of 2 different ARM architectures, ARM v6 and ARM v7. So those are 2 different instruction sets that offer some kind of backward compatibility. But those are 2 different levels of architecture. So those are 2 specifications. And for the specific case of ARM v6, ARM has designed an ARM 1176 core. That's, again, just some design that has been bought by Broadcom, integrated into the now popular BCM 2833 SoC, which is used in the Raspberry Pi board. So what Broadcom did is buy this core and put some additional peripherals around it and sell you the chip. So this includes the famous or infamous video core stuff, but many other peripherals as well. And there are below some other examples as well. From the ARM v7 architecture, ARM designed both the Cortex A8 and Cortex A15 that provide different levels of performance, power consumption, and so on. But from the outside perspective, they behave the same. They implement the same instruction set. And for example, TI took the Cortex A8 to do the AIM33.5X SoCs that are used, for example, on the popular BeagleBone platform. Samsung took the Cortex A15 to design the Exynos 5, which is used on a new development board called the Andale. And there are even some other silicon vendors, and Marvell is one of them, who decide to not buy the ARM core, but instead buy the right to re-implement a different ARM core that is compatible with the ARM v7 architecture. So for example, the Armada XP SoC, on which I've been working for some months now, uses the PG4B ARM core, which has been entirely re-implemented by Marvell. So depending on the chip you're using, it's either an ARM core that has been designed and written by ARM, or it may be also written by the silicon vendor himself. So this means that there will be a very huge variety of silicon system on chip, available on the market. There are already hundreds of licenses of ARM, and each of them do several families of SoCs. If any of you have already tried to understand the entire family of SoCs, even inside a single silicon vendor, like try to understand all the SoCs that TI is selling or all the SoCs that Marvell is selling, they are so numerous that it's very complex to understand what SoC is designed for what markets, what features is in each SoC, and so on. So there's a huge variety, and that's kind of typical to the, kind of specific to this ARM architecture. So it makes it really fun, but also means that, well, you need to handle this variety. So in a very high-level view, when you work and interact with ARM hardware platform, be it your phone, your TV, or your development board like the BeagleBone or the Raspberry Pi or any other ARM-based platform, it's very important to always have this vision of what you're using. So you're using a board that has several components on it, like some RAM, some flash, some Ethernet connectors, sometimes some additional, I don't know, I2C thermometers or accelerometers or any other components. So those are the onboard peripherals in purple here in my diagram. And of course, amongst those components that are visible on your PCB, one of them is probably the most important of all. It's the SoC. So it's one chip. From the outside, you can only see just it's one chip with many pins that are usually below it, so you can't even see the pins. And this SoC, which in the case of Raspberry Pi comes from Broadcom, for example, integrates many peripherals inside it. So again, serial port controllers, graphics controllers, Ethernet controllers, and many other things, and an ARM core. So that's really the design that you have. And the Linux kernel needs to do all those levels of different hardware components. It needs to handle the ARM core. It needs to handle the peripherals inside the SoC and the peripherals that are on the board. And of course, do that by sharing as much code as possible because we don't want to duplicate code in the kernel. Another aspect of the ARM architecture is that, well, I said no standardization, but I should have said not too much standardization. It's kind of part of the ARM philosophy, or at least my understanding of the ARM philosophy, to leave a lot of freedom to the SoC vendors. So ARM sells the ARM core, but then leaves basically complete freedom to the SoC vendors to integrate the peripherals in their SoC. So they don't say you should use this bus or organize the peripherals this way or use this sort of peripherals, something like that. They just give them almost total freedom. So that's nice because silicon vendors come up with interesting ideas. They go in various directions. They can maybe fill the needs of various markets by integrating various types of peripherals, providing various solutions in terms of cost, performance, power consumption, and so on. So it's pretty nice. But it also means that from a software perspective, each SoC is different, and you need to write some code for each SoC to support the different peripherals. So there's no standard for the devices, for the management of clocks, for the management of pin muxing, for the management of hierarchy controllers, of timers, even though some of those things are getting standardized as we go in the new generations of ARM cores. It's still quite free for the silicon vendors. So when you take a Marvell SoC and a TI SoC and a Broadcom SoC, the way you configure the clocks, the pin muxing, the hierarchy controllers is entirely different. And so that's one part of it. And the other part of it is that contrary to what's now common on the x86 architecture, there is no mechanism to enumerate the devices available inside the system on chip. So on x86, typically, most of the devices sit on a PCI bus, and the PCI bus provides a dynamic enumeration capability. So you can ask your PCI controller, hey, what's on the bus? And it's going to tell you, oh, on slot 0, you have this thing that's a graphics controller for NVIDIA with this identifier, and so on and so on. In slot 1, you have this Ethernet controller from Intel, and so on and so on. Inside the ARM SoC, nothing like that. There's no enumeration mechanism. You have to know in advance that at this specific address sits this specific peripheral. At this other address, there is this other peripheral, and so on and so on and so on. So it's, again, a lot of information that the software needs to know to be able to run on such platforms. So now that I've given this background about the ARM hardware, let's look a little bit at how it's supported inside the Linux kernel originally. So that's why I'm putting all here, and I'm going to explain some of the details, some of the changes, that have been brought to this organization. So in the Linux kernel, of course, most of the code is architecture independent, and I'm not going to be too much interested during this talk by the architecture independent parts of the kernel. So I'm going to be focused on the ARM directory, which, as you might guess, contains all the ARM-specific code. And inside this directory, we could classify things in two big areas. We have the parts that we could call the core ARM kernel, the things that take care of the ARM core itself, so that knows how to configure the MMU, how to manage the interrupts, how to boot the system, and really the things that are core and not specific to the peripherals of a given SoC. So this part is, I would say, relatively small in size. Well, at least it doesn't grow too much because it's specific to the ARM core itself. So it's common to all the SoCs that exist. It's pretty well maintained. ARM themselves, the company, and their engineers do a lot of work in bringing that constantly up to date with the new ARM cores that are being released. So it's pretty well maintained, relatively small compared to the rest. So that's what we have in ArchARM, kernel, ArchARM, 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 boot, and so on. And then next to that, we have a lot of SoC-specific code because, as I've said, we need to support the differences of all the SoCs that are supported by Linux. And this is done in the Linux kernel through the ArchARM Mac something. So you have one for, I don't know, the IMX from Freescale, one for the OMAP from TI, another one for the S3C chips from Samsung, and so on and so on. And are currently probably somewhere between 50 and 100, maybe 50, 60 directories with this name, each taking care of a specific SoC or family of SoCs. So inside these directories, we typically add all the SoC-specific code, ending the clocks, the pin muxing, registering all the devices that are present inside this system on chip. Like, okay, on this system on chip, there are 4 serial port controllers at this address, this address, this address. On this other variant of almost the same SoC, but not exactly, there are only 3 serial port controllers, but there are 2 network interfaces. And this other one, there are 2 serial ports, but 4 network interfaces, and so on and so on. So under all this description of the hardware. And then in addition to that, those directories typically contain what people familiarly call board files. That's a C file that describes a particular hardware platform. So if we go back here, so we typically have one directory for each of the SoC families. So we would have one for BCM2835, we have one for the OMAP platforms, we have one for the Exynos platform, another one for the Marvell platforms. And then inside those directories, we would have had one board file for each specific hardware platform that you have. So here I only illustrate with one board for each SoC, but of course you can imagine that many people are buying like, I don't know, the TI IM 33X, 5X chip and develop and produce many different hardware platforms. So I don't know how many board files did exist in the Linux kernel, but several hundreds of them. So it's a lot of C code, pretty boring, hard to maintain, and so on. And the other part of the, of course, very important part of the support for hardware are drivers. So the device drivers in Linux are mostly architecture independent, so they sit not in the Arch directory, but in drivers. And that's going to be quite important because, as we'll see, one of the change that occurred is trying to move more things into driver subsystem and therefore in the drivers directory. So what was the issue, or at least my understanding of the issues? Again, as you've seen, I'm just mostly involved in bringing into mainline the support for 2 Marvell SoCs, so I don't necessarily have a big vision of everything that's happening in the ARM kernel world, so it's my vision of what has been happening. But essentially, in the recent years, the number of ARM SoCs has literally exploded. Most basically know everybody has ARM SoCs around that can run Linux. And those SoCs have become more and more complex. So it's not only the number, but also the complexity of those SoCs that has increased quite a lot. And the historical maintainer of the ARM architecture, Russell King, got more or less overflowed by the amount of code that is specific to each and every SoC that needs to be reviewed before being brought into mainline. And because he couldn't review this huge amount of code, and it's really difficult because it's specific to each SoC, you have to know the specific details of this SoC from this vendor, from this other vendor, and so on. So it's quite complex. So basically what started to happen is that the sub-architecture maintainer, so what we call sub-architecture, are the families of SoCs. So basically in the ARM community at the kernel level, you have a small community around the OMAP platform, a small community around the Marvell platform, a small community around the, I don't know, Broadcom platform, a small community, and so on, specialized around one SoC or a family of SoCs. And so those communities, usually each of them have a top maintainer. They started to send their code directly to Linus, basically bypassing Russell, who couldn't handle the load of reviewing all this code. So it's allowed the code to flow into the kernel, but the problem is that nobody was then at this point having a cross view of the different sub-architecture. So nobody was here to detect duplicated code or common patterns that were not being solved by a common infrastructure and things like that. So it was really lacking of a maintainer looking after all those SoC families. So code duplication and, more importantly, missing common infrastructures leading to some maintainability problems and so on. And this problem that became more well known to the entire, I would say, open source crowd in March 2011 when Linus said, okay, this whole ARM thing is a pain in the ass. you need to do something about it. So it's kind of the starting point. Well, it started a bit earlier, but it was kind of accelerated the need to move and make a few changes to and how the ARM architecture is managed in the Linux kernel. And the other issue, or I'm not sure it was an issue, but a new need that appeared is the need for multi-platform kernel. So on x86, it's pretty conventional, or everybody is used to building a single kernel image that boots basically on all PCs that exist. So provided, of course, you have the right drivers, you can build one kernel, ship it as the official kernel for your foobar distribution, Ubuntu or Fedora or whatever your favorite distribution is. You build one kernel, you ship it, and you know it's going to boot on all laptops, all desktops, all servers, and so on and so on. So it's one image fits all. That's pretty good for distributions. On ARM, that's typically, or that was typically impossible. So you could build a kernel that would boot on different boards that use the same SoC, so the same processor, but it was absolutely impossible to build a single kernel that would boot on a OMAP platform and a Marvell platform. Totally impossible. So if you are a distribution maker or a system maker and you want to sell or provide a system that will easily boot on ARM-based tablets or ARM-based laptops or ARM-based netbooks or whatever type of hardware you care about, basically you had to build one kernel per hardware platform you wanted to support or family of hardware platforms you wanted to support. So it's kind of annoying. And if you've looked at the Ubuntu support for ARM, for example, they have different images or different kernels depending on the hardware on which you're going to run this distribution, precisely because of this problem. So it's not nice, and as ARM SoCs are no longer being used only in deeply embedded applications where you don't really care about distributions, but are now also being used in more consumer devices where you want to allow people to change their system, update it, add more applications, and so on, it started to become a problem. And so one of the issues to solve was how to add multi-platform support to the ARM Linux kernel. Which means how can we build a single kernel image that will boot on as many SoCs as possible and therefore support as many hardware platforms as possible. So basically, those are, I would say, the two main issues. There are probably many more that I'm not aware of, but I think that's the main two ones. So now let's look at the changes that took place in the ARM community. The first change, and I don't know if it's the most important one or not, but certainly an important one, is the change of maintenance process. So as I was saying, the sub-architecture maintainer were pushing their code directly to Linux, and this has changed. Now we have a team of 2 ARM SoC maintainers. So Arne Bergman works for Linaro now, he used to work for IBM, and Olaf Johansson, who, as far as I know, works for Google. And those 2 guys, they take care of taking all the ARM SoC-specific code from the different sub-architecture maintainers. So now the OMAP maintainer, the Marvell maintainer, the Broadcom maintainer, and so on and so on. They push their code to Arne and Olaf, and they do a review. Well, the review process happens before that, but basically they take care of having this cross-SoC view, trying to identify where things should be done, are kind of similar between different SoCs. Maybe we need to find a common solution for them. Maybe we need to create a new subsystem that will solve this specific problem, and so on. And at least from the contribution I've done on the Marvell SoCs, I see it work pretty nicely. I mean, Arne and Olaf review a lot of patches. They do a lot of comments, try to point similarities with other families of SoCs and so on. So it works pretty nicely. At the moment, for example, I'm working on the PCI support for those Marvell SoCs, and I work very closely with the guy doing the PCI support for the Tegra SoCs from NVIDIA. So we look at each other's code, trying to find common patterns, sharing infrastructure, and so on, making drivers more similar. So I see it working. So that's one change. Now all the code flows into a tree, a Git tree called ARM SoC. where all the conflicts are resolved, all the ARM-specific discussion happens, and this ARM SOC tree is then merged upstream by Linus. So we now again have this cross-SOC view. And in this team of maintainers, and generally in the different other changes that we've seen, there is a fairly important role of a consortium called Linaro. It's a consortium that into which many ARM silicon vendors participates, probably not enough, certainly, but some SoC vendors. So ARM themselves, but I think also TI, I don't want to give wrong names, but I think Samsung as well, and some others. They put engineering resources into this consortium, and instead of being only focused on getting the support for their own SoC into mainline, they care about the bigger picture, how to make the kernel itself better to support the ARM architecture. So they try to design new subsystems and so on, and I'm going to present some of those. So this consortium has played a quite important role in those changes. So that was about the first change. The second important change, and probably the one that is going to be visible to most of the people, because it doesn't only affect the kernel developers, but even the users of the kernel, is the introduction of the device tree in the ARM architecture. So as I was saying, the devices inside an SoC and most of the time on the board, so outside the SoC but on the PCB, cannot usually be enumerated. So you have to know in advance which devices will be there, on which bus, how to configure those devices, at which address, and so on. And the old way of doing this description was using C code. So a lot of this SoC-specific code and board-specific code that I was referring to earlier was here to register what is called in the kernel terminology platform devices. So those are devices, and the kernel has a nice uniform device model to represent all the devices in your system, be they USB devices, I2C devices, USB, PCI, and so on. And one specific type of devices are the platform devices. Those are the ones that are directly within the platform itself, like the peripherals that are inside the SoC. So typically, a lot of code was looking like this thing. At some point in the kernel initialization, once we had detected the board on which we were running, what is the SoC, we would register many peripherals this way. So here we're registering the USB device controller of an 8091 SoC from Atmel. So basically we have a lot of C code that says, okay, in this platform I have a USB device controller. The driver is identified by this name. So actually the string here is very important because that's this string that allows us to associate the device with the corresponding device driver. And this device is located at this address. That's the RQ. I think my laser pointer is dying. Too bad. So here we have the base address, and here the RQ. And those informations are communicated to the device driver, which then knows, okay, there's one USB gadget controller on this platform of this type, at this address, at this RQ. So we had a lot of this kind of boilerplate type of C code. It was working, but apparently it was seen as not being really nice to maintain. So the ARM community has moved towards a different description of the hardware using a specialized language called the device tree. That's a solution that has been used since many years on PowerPC and is also used in other architectures inside the kernel like Microblaze, of course the new ARM64 architecture, the Extens architecture, OpenRISC, and maybe others in the future as well. So basically, instead of doing C code, you describe your hardware with a specialized language that looks like a tree, hence the name. So here I took a short extract of the device tree that represents the BCM2835 SoC. So that's the SoC inside the Raspberry Pi. So the kernel support for this hardware is very minimal, so that's why there are not many peripherals here. But basically, I won't detail the entire language, but what we describe is in this SoC, we have one device that is an interrupt controller that sits at this address, and the string here identifies the driver that corresponds to this device. We have a UART controller with strings, again, identifying the driver that will be responsible for managing this device, the interrupts, the registers, and so on and so on. So we describe what's inside your hardware, basically. And this file describing the SoC, so the chip, gets inherited by a file describing the board. So this one describes the Raspberry Pi itself. And at the moment I made the slides, only the UART was supported, so it's pretty easy. So here we say, okay, my board uses a BCM2835 SoC, so I inherit from that. And I overlay on the previous tree, I overlay this one. So basically, I add an information about the amount of memory in this system, and here I override the property status. So you see here, status was disabled to say, okay, there's a UART controller, but it's not used. And here we say, oh, in this board, this UART controller is actually wired to the outside world, and so we want to enable it. And from these two files, there is a compiler called the device tree compiler, which is part of the kernel sources, that will produce at compile time a binary representation of these device trees. That's called a device tree blob for DTB. And this DTB will be passed to the kernel by the bootloader. The kernel will parse it and find there the description of the hardware and therefore be able to instantiate all the available devices. So essentially, it's a bit more complex than that, but essentially we're replacing a C-based description of the hardware by a more a specialized language description of the hardware called the device tree. So if we look at, I'm going to jump here and be back on the previous slide after that. So in the old style way of, before the device tree, on ARM you would be building a kernel that includes as C code the description of all the peripherals inside the SoC and on the board. And the kernel would know on which platform it gets booted thanks to an identifier called the machine ID that gets passed by the bootloader. So if you could build a kernel that supports multiple boards as long as they use the same SoC, and the bootloader will tell the kernel, oh, you're being booted on the Raspberry Pi, you're being booted on this or this platform. And then the kernel would know, okay, I'm on the Raspberry Pi, I'm going to instantiate this and this and this and that. Now the hardware description is kind of outside of the kernel in this device tree blob. So when you boot your ARM kernel from your bootloader, you actually need to load two files in memory and give them to the kernel. So the kernel image itself, which no longer includes the description of the hardware. It, of course, includes device drivers, but not the description for a specific hardware platform of which devices are present and where and how they are connected and so on, only the device drivers. And then next to that, you load into memory a device tree blob, and then you boot your kernel. And when you boot a kernel, you tell it where is the device tree blob, it will parse it and find the available hardware. So we separate out the hardware description, basically. There is for those using some of the old platforms, there is a compatibility mode because this solution requires support from the bootloader. Your bootloader has to know about the device tree, be able to load it into memory. Sometimes bootloader even need to make changes to the device tree to adjust some parameters, like say the MAC address of your network interfaces or some other properties. But there are many bootloaders around that still don't have device tree support, and for those, the kernel is capable of being built with a device tree blob integrated into it. A bit like you would build it with a firmware integrated into it. You build it with device tree integrated into it, and from the point of view of your bootloader, it's still just a kernel image, just one file as it used to be. But from the point of view of the kernel itself, it really just parses a device tree blob like it would do in the normal case. So it's one of the big change, and progressively, so all of the new platforms in the Linux kernel have to use the device tree. So all the new ARM platforms need to use the device tree, so otherwise you can't get in. And all of the existing popular platforms are being migrated. So OMAP things, Marvell things, many existing SoCs are being converted over to the device tree. And as you can see here, it has an impact not only at the developer level, but also at the user level. And this, as I've shown on the example of the Raspberry Pi, there is inheritance that takes place. So you write, in the case of the Raspberry Pi, one device tree that describes the SoC, and then another that describes the board and inherits from the SoC, but adds some more board-specific information. And this inheritance is actually quite practical when you have a family of SoCs where you have multiple types of processors that have some commonalities but also some differences, and that's the case in the Armada 370 and XP SoCs that we're taking care of. So that's a family of SoCs. We have the Armada 370, that's one chip you can buy, but the Armada XP is actually 3 different SoCs. Some of them have 2 cores, some of them have 4 cores, some of them have like 4 PCI interfaces, some of them have 10 PCI interfaces, so it's quite complex. But thanks to the device tree organization, we can factorize the common parts in the description of the hardware, and then put the more specific parts into different files. So here you see, for example, if you're using the OpenBlocks platform, it's a nice small box that uses the 2 cores variant of the Armada XP called the 78260. So it inherits, this board inherits from the 260, which itself inherits from the Armada XP, which inherits from Armada 370 XP, and those different device tree add more hardware description until we reach an entire description of the hardware when we come at the board level. So it's quite nice. So that's the second change I had. The third change, which I think I already mostly said everything about it, the need for multi-platform kernel. You want to build a single kernel image that can boot on as many platforms as possible. So the device tree is one part of the answer to this, but it's only a fairly small part of it. If you put the hardware description outside of the kernel, then you can pass different hardware description and have the kernel adapt to it, but it's not the only problem that had to be solved. There was a lot of conditional code inside the kernel that is at compile time. You would decide, do I integrate the support for this SoC or that one? But you couldn't have both at the same time, so you need to replace a lot of conditional at compile time by conditional at runtime to detect, okay, I'm on this SoC or this board, and at runtime decide what to do. There were also conflicting APIs, like if you build the kernel for OMAP, it would implement a function foobar, and if you build the kernel for Marvell, it would implement the same function called foobar. So of course, if you build one with just OMAP or one with just Marvell, it works fine. But if you build a kernel that has both together, you have conflicting symbols. So all those kind of things needed to be sorted out. And now it starts to be possible, I think since 3.7, to build a single kernel image that builds on different platforms. Of course, not all of the ARM platforms support this capability, but the new ones do. So it's kind of the device tree. If you want to add the support for a new SoC in the Linux kernel, it has to support this mechanism. So basically, it is possible to build one kernel that will boot on all ARMv4, ARMv5 SoCs, and a different kernel image for ARMv6, ARMv7. So it's not possible to do one that does everything, but with 2 kernel images, you would solve the problem for most of the ARM platforms around. So that's another change that is taking place, and again, as I said, since 3.7, it's live and actually works. Another change is the introduction of the pin control subsystem. Time is passing. So basically, in these ARM SoCs, you have so many peripherals inside that you don't have enough pins on the processor itself to use all the peripherals that are inside the chip. So you need to decide, and that's configurable by software, to what functionality each pin of the SoC will correspond. So here I have chosen some example. Let's say you have UART controller, SPI controller, and I2C controller, and you have 2 pins. Well, of course, you can't make use of all these features at once. You have to decide, I want to use either the UART or the SPI controller or the I2C, or use those pins as normal GPIOs. So that's software configurable. So if it's software configurable, we need code inside the kernel to do that. And in the, I would say, old kernel, basically each ARM subarchitecture was solving this problem in its own way. So each subarchitecture had its own API, its own way of describing the pins, its own way of doing this configuration. So lots of code duplication. Each device driver had to somewhat describe which pins it required in an API that wasn't the same depending on the SoC you were using, so not nice. So there was a lot of code in Arch ARM and no factorization happening. So one of the things that happened, and it's mainly being driven by Linus Walege, who works also for inside the Linaro consortium. So when I said they played an important role here, that's one example. He designed a pin control subsystem, so that sits in drivers pin control. So that's moving stuff outside of Arch ARM into proper drivers. And this subsystems allows the implementation of pin muxing drivers. So those are the yellow boxes at the top left. So for each SoC, you implement a driver that describes, I have those pins, and how I change the configuration between pins. And then the device tree can define the possible configurations of pins. So for example, in my case here, I would say in my device tree, if you want to use UART3, then you have to configure pin 1 and pin 2 in such or such mode. And then in the board file, you would say, on this board, I make the choice of using UART3. So I won't be able to use SPI1 and I2C0 because the pins are already used by some other device. So it very nicely splits the configuration of the pins, how to actually change it and modify the registers from the description of the hardware. So it's a quite complex subsystem, but here the idea is that by moving things outside of Arch ARM into a proper subsystem, we factorize more things, more code, and we also look at the other drivers doing pin muxing. So we find common patterns, we factorize them out, and so on. So it's really a good improvement, this pin control subsystem. On more or less the same idea, the clocks. So in the system on chips, all the peripherals are driven by one or more clocks. And those clocks are organized in a tree, and many of them are software controllable. So for example, to save power, you can gate certain clocks, or you can change their frequency to, well, reduce the power consumption. So since they are software controllable, you need, well, code to manage them. And until now, the only mechanism in the kernel to do that, or at least at the ARM level, was an API. So the device drivers could do get a clock, enable a clock, disable a clock, and put a clock, but that was just an API. And each ARM subarchitecture had its own implementation of this API. So OMAP had its implementation of CLK gets, CLK enable, CLK disable, CLK put, and so on with other functions. And the other SoC families had their own implementation as well. So first of all, the obvious problem is that it does not work at all for multiplatform kernel because you have multiple implementation of a function that has the same name. So obviously, if you compile and link them together in the same kernel image, boom, it does not even link. But further than that, it does not allow code sharing, have common mechanisms, and so on. So a common clock framework was added in the kernel in 3.4 and device tree bindings for it. So mechanisms to use it from the device tree were added in 3.6. So it's pretty recent. Basically, what this framework does is it provides a single implementation of this API, which basically for the driver hasn't changed that much, except a few details. So drivers can still get a clock, enable it, disable it, and do various things around the clock. But besides, beyond that, there is one single implementation of it, the common clock framework, and each SoC family needs to bring its own clock drivers. So for example, on OMAP, you have a certain number of clocks that are configured through special registers. There is one or several drivers to manage them. There are also basic clock drivers that are available for simple clocks that you can just enable, disable, or simple divider clocks or fixed factor clocks and so on. So it really allows to factorize code for the management of those things. And again, all this code was originally in Arch ARM, specific to each SoC family, and is being migrated in drivers/CLK. So it's not only about moving code, but by moving code into a common directory, you also encourage developers at looking at the other clock drivers and finding commonalities, reusing existing patterns, and so on. So sometimes people don't really see that just as moving code, but it's, I believe, really an encouragement in looking at the other drivers that's there. So it happens for pinctrl, it happens for clock, and it's going to happen for more things. And then this common clock framework allows in the device tree to declare the clocks that you have. So it's actually describing your hardware, what's your tree of clocks, and then associate in your device tree each device with the relevant clocks. So then your device driver can just do, I want my clock, and then it's described in the device tree, oh, but the clock of this device is this one, which requires this one and this one and this one, and it will automatically take care of enabling the right clocks. So it's pretty nice system. So it's summarized here, the clock framework. On one side, you have the device drivers, like your Ethernet controller driver, your serial port controller driver, your I2C controller driver. Each of those drivers are driving a specific device that needs one or several clocks. So they use the clock get, clock put, clock disable, clock enable API provided by the clock framework. As an input, it gets the device tree, which tells the clock framework what clocks are available, their name, and the association between devices and clocks. And then behind, without the device drivers knowing about that, it talks to different clock drivers that are either specific to your SoC or more generic. And that solves the problems nicely. And also isolates the device drivers from the specificities of your SoCs. If I go back to the beginning here, those green boxes, they could be the same between different SoCs of different vendors. Typically, the discussion about the 3D acceleration, you see that the PowerVR core is used on Texas Instruments chips, but also on others. But it's the same for some USB device controller and on other things. So a peripherals is not necessarily specific to an SoC, and there is some reuse at the hardware level between SoC vendors. So you want for those peripherals to have a single device driver in the kernel. And to make it possible, you need to kind of make the device driver itself independent from how this peripheral is inside the system on chip. So you need to separate the pin muxing thing, separate the clock thing to make the device driver reusable between different SoCs using the same peripheral. Another change, which I think I've been highlighting already, is the move of code from Arch ARM into drivers. So as I said, it's not only about moving code just to make the amount of code reduce in Arch ARM and have more stuff in drivers, but it's also that by categorizing drivers by type, you will have more developers looking at the different drivers of the same type and finding commonalities and helping maintenance and so on. So the RQ controller drivers are moving in drivers RQ chip. The timer drivers are moving in drivers clock source. The PCI host controller drivers are moving in drivers PCI host. The clock drivers are moving in drivers CLK, PinMux, same thing, it's moving over. So that will make things nicer in the future and reduces the amount of code in Arch ARM. So to finish, just to illustrate the work we've done on the Armada 370 and XP, it's going to be pretty quick here. To show the progression of work we did, we started with Linux 3.6 by adding the basic support for those SoCs. So when I say basic, it's really basic. You could simply boot, have something on the serial line, no storage driver at all. Everything had to be with a RAM file system, and that's all. So we had just a minimal device tree, basic initialization C file, a timer driver, RQ controller driver, support for early print-K, which gives you messages when the kernel is booting very early, and a serial port driver. But in fact, for serial port, we had nothing to do because this particular SoCs use the 8250 UART compatible peripherals. So with just 10 patches, we had the beginning. It went in 3.6. In 3.7, we added more basic infrastructure, the pin control driver, the GPIO driver, and some specific stuff to Marvell as some things that we call the address decoding code that allows to configure physical addresses. Well, it's kind of complicated. So we had 35 patches to put that in place. Then 3.8 was quite big for us. We added L2 cache support, the clock drivers and clock tree description, as I said, the SMP supports, coherency support, so it allows when you have multiple CPUs to make sure that they share the same view, but also between the CPUs and the IOs. We added a network driver that was completely new, and then we enabled SATA support and XOR support, and those were pretty easy because Marvell reused the same IP blocks as earlier versions of their SoCs, and they were existing drivers in the Linux kernel. So we just had to basically enable them in the device tree, and that was about it. So it really shows that reusing drivers actually works. So we had 99 patches going into 3.8, which isn't released yet, but should be soon. And for 3.9, we'll be adding some more things. RTC, USB, SDIO support, but here it's also pretty easy. We already have the drivers inside the kernel. The hardware units are the same than previous version of the SoC, so we just reuse the drivers as is with almost zero change. We added RQ Affinity support, so it's kind of nice when you do SMP. Local timer support, it's also SMP related. And we're hoping to bring PCI support as well. So hopefully this is going to be in 3.9. I don't know, should be going 30, 50, maybe between 20 and 40 patches, depending on how many things we can merge. So in basically 4 versions of the kernel, we managed to push quite a lot of features to support those new SoCs, which is nice. I have 1 minute left. So my few recommendations into getting an ARM SoC in mainline: throw away vendor BSP code. It's crap. It usually does not use the device tree, does not use any of those infrastructure that's set up by the kernel. So Marvell does have a BSP. We haven't ever looked into the code for this BSP. It's almost useless. Start small. They have some communities, for example, around the Allwinner A10, A13 SoCs that have been doing a lot of Linux work on their side without submitting anything. And they kind of apparently were waiting for everything to be ready before submitting. But then at this point, you realize that you did something wrong, you used the wrong interface, and you have to redo a lot of work. So start small, submit early. Comply with the latest infrastructure changes. I think I described some of them. Reading and posting to the Linux ARM kernel mailing list is mandatory. You have to follow that almost on a daily basis to keep track of what are the latest infrastructure changes, the good practices. Listen to review and comments, be patient and persistent in retrying, and look at the recently merged sub-architectures. There is really a wide range of sub-architectures in the ARM kernel, and not all of them are up to date with all those changes. So pick the right ones. So I've mentioned a few of them here, but look at which architectures are really active and up to date before taking some code as an example. So you remember in March 2011, Linus said that's a pain in the ass, this ARM stuff. And more recently, in August 2012, he said over the last year, ARM has gone from a constant headache every merge window to an outstanding citizen in the Linux community. So it sounds like his opinion has changed quite a bit in just a year and a half, which is nice. Questions? Yes? Okay, so the question is, I said with the pin control thing, you can describe the pin muxing in the device tree, which means, does that mean it's a compile time only and can be changed at runtime? So it can, to some extent, be changed at runtime. For example, there are some SoCs that need you to change the pin muxing when you go into suspend and then when you resume, things like that. So there is some mechanism to do runtime changes of the state of each pin. But as far as my understanding of the pin control system goes, there isn't really a support for completely changing the mixing at runtime, like switching from using an SPI controller on those pins to using something completely different. It's not, maybe some people are trying to work on this, but it's not really part of the initial design and usage of it. So it's mainly static. Some other questions? Yes, please. How do they relate to GPL? So at the moment, the device tree files are part of the kernel sources in Arch, ARM, boot, DTS, at least the ones that people want to submit. So those ones are licensed under the GPL. I'm not sure what's going to happen with a device tree that will be outside the kernel and shipped as binary only. I'm not exactly sure what's the licensing status. I'm pretty sure it's going to be raising a number of issues and questions about what's their licensing, or vendors providing a binary only version of a device tree. But it's, having a binary version only of a device tree is not too much of a problem, because it's the text version and the binary version are kind of close together. So it's not like source code and compiled code, where it's very hard from compiled code to get back to source code. Here it's pretty close. So it will not be that big of an issue, a practical issue, but there will certainly be some licensing questions yet, but I don't have the answer.